This is a very important section, factors that affect solubility. I'm going to take my time in the Zoom lecture, but here I want to just get the facts down. Know that this is all based on experimental observations. It is not a model, it is not a theory, and the guiding principle is like dissolves like. There are different types of solute-solvent interactions, and they're based on what you learned in Chapter 11. The stronger the attractions, the greater will be the solubility. We can have polar liquids. They tend to dissolve in polar solvents. We have nonpolar liquids, and they tend to dissolve in nonpolar solvents. We use the terms miscible and immiscible. Miscible means it mixes in all proportions, and we use the infinity symbol, something like water and acetone, hexane and heptane. If we use the term immiscible, the substances do not mix. An example would be hexane, C6, and water. Hexane is nonpolar, water is polar. You can see the picture here, and you can see a distinct line in between the two, kind of like Italian salad dressing. And you can also see that density is going to impact the layer order. Water has the density of 1, heptane has the density of 0.659. I listed these. These are not to be memorized. Please do the homework until it starts to flow. You learned in Chapter 11 how to assign intermolecular forces, and you can see these are grouped in that manner. Again, up to you. Now, a little bit more about the dipole-dipole forces. In Chemistry 1210, in Chapter 11, we talked about single molecules. There was a table where it listed dipole moments and boiling points. When we're in Chemistry 1220, it will involve multiple molecules, and you're going to have to distinguish between different sorts of pairs. Acetone, and again, in lecture I'll go through this, and chloroform. There's definitely some dipole-dipole forces there. The other thing to mention is the ion dipole. Now, if you had me for Chemistry 1210, I've been sort of shoving this down your throats ever since the original chapter. Ions do not exist naked, like sodium plus is surrounded by water molecules in aqueous solution, and that's ideally. But indeed, there are ion dipole forces. They can lead to something called ion pairing. It'll be discussed as the Van Hoff factor, a lowercase I, as we get deeper into the chapter, and they are going to influence colligative properties. Now, things to remember about this section. If you have hydrogen bonding present, the more OH groups you have, the more soluble things are going to be. I use as an example hexane versus glucose. Notice hexane is just carbon and hydrogen, and there is its formula. It'll have boat and chair configurations when you take organic. Here we have only London, and it is totally insoluble in water. Just does not mix. What if glucose, same number of carbons, same number of hydrogens, but now 6 oxygens, and you can see these OH groups. These are hydrogen bonding sites, and it makes glucose immensely soluble in water. Now, this is an exaggeration. There are polyols and things like that, but it is a principle where the more hydrogen bonding you have, the more soluble something will be. The other important point, and this is where I learned, teaching, there are tables, but you need to really emphasize them in class. Here we have different alcohols. This is a C1. It goes all the way down to C6. Notice they're going to tell you about the solubility in water, which is polar, and the solubility in hexane, which is nonpolar. All right? So essentially, we will see that as long as we have a few number of carbons, we are very miscible. But as our number of carbons tends to increase, our solubility is going to decrease. Perfect midterm question. I mean, I have to almost like put this on a platter for you. If I walk over to the C6H14, what we will see is that only methanol is going to dissolve, but we will see miscibility with all the other alcohol materials. It's a fact. It's an observation. Again, a midterm question. Now, have to mention this because when you look at a network solid like silicon dioxide, that is sand at the beach, or what it had once it has been heated, it is window glass, insoluble in water. We know that when it rains, our windows do not leak through the glass. So again, a little bit silly, but hopefully make things stick. Real life vitamins. There are certain vitamins we need every day, like the water-soluble ones that are polar, and others that are fat-soluble that are not as important to have in our daily diet. Vitamins A, D, E, and K, they are primarily non-polar. They are fat-soluble. They only have one non-polar group. So when you eat these vitamins, they will stay within our body. When we have orange juice, let's just pick on vitamin C. Notice vitamin C has many, many different sites for oxygen, dipole hydrogen bonding. It's going to be very soluble in water. And to put it mildly, when you drink orange juice, it comes back out. I don't know how else to say that, all right? The one sitting here on the bottom, this is the no-calorie fat developed by Procter & Gamble. It's called Olestra. And notice it has many polar groups on it. They use this to make something like fat-free potato chips, so you could eat as many as you wanted without the calories. The only drawback, great intestinal distress. So not a product that had great success in the marketplace. There's another factor in solubility called pressure. Solids and liquids, there is no effect. But if I have a gas, it is really governed by Henry's law. Please do the calculation. It's important. We have carbonated beverages. We have people that do skin diving, scuba diving. So really, these are real life types of issues you could deal with. When you think about gas solubility, please think of the piston. As the piston goes down, it will force more gas into solution. The bottling line at a brewery, it's going to be under a little curtain of pressure so they can carbonate the beer before it gets capped. Real life examples again. I just come from the real world, and as you can see, many different things are affected by pressures and molecules. And again, the one that really has always caught my eye is the aquatic, how different species in water need different minimums amounts of oxygen. And of course, if you're going into medicine, there's the oxygen level in your blood. Temperature effects on water. Okay, why is this important? Well, we can have a solid and we want to turn it into an aqueous solution. What has been observed is that if we add heat to a solid to make an aqueous solution, our solubility is going to increase. It's Le Chatelier that we will cover in another chapter. Or let's say the solid, when it dissolves in water, it's going to give off energy. It is therefore going to also be explained by Le Chatelier. All right, so you should be able to label this. The first one is an endo reaction. The second one is an exo reaction. It comes to us from chapter 5. You can see that if solubility increases with temperature, I'll just pick on potassium nitrate, you can dissolve more solid in the water. If you have, instead of a solid, if instead you have a gas, there is a general rule about gases that dissolve in water. If they can hydrogen bond, if they can ionize, or if they can react, they will be more soluble in water. And finally, more of a math question. Let's say, hint, hint, that someone on a midterm wants you to say, how much of lead nitrate will dissolve in 250 grams of water at 30 degrees. You will be given the chart, and it's the same chart I had in high school, and you all know how old I am. What you want to do is find 30 degrees, because that's what it is, and you want to read up on 30 all the way to lead nitrate. Once you hit that line, what you want to do is read over to the left on the y-axis to see what is the solubility grams of salt in 100 grams of water. And like I said, it is the same chart that I had in high school. Some things never change. So if we can put, say, 66 grams of lead nitrate in 100 grams of water, the question is, how many grams of lead nitrate will dissolve in 250 grams of water. There is a lot of basic algebra in Chemistry 1220. Sometimes we think it is called algebra chemistry because we just solve a lot of problems. So if we do the math, we would say that it would have 165 grams of lead nitrate would dissolve in 250 grams of water. They may ask you about sig figs, and based on how this is written, 2 sig figs, we can only have 2 sig figs in the answer. 1.7 times 10 squared grams of PbNO3 for 250 grams of water. Now, I've recorded this a number of times and it's always too long, so I don't mean to speak so quickly. Please come to the Zoom lecture, and I cannot stress more about you doing the homework in this section. It will ensure you a superb grade on your midterm.